So now we are coming to our next example, that is example number 14. And now we will introduce the symmetric group. So let X be any set. A set, of course, non-empty set we should take, non-empty set, and consider Symmex to be a map from X to X such that, so I am defining another set with the help of this set X, and we denote it as Symmex. So F is bijective map from X to X. So Symmex is a set containing all the bijective maps from X to X. Now we know one thing, that if we compose two bijective maps, then the composition will again be a bijective map. So what is composition of map? Suppose I take one map F1 from X to X, X is a set, and I take another map F2 from X to X, then the composition of map being, if I have an element X here and the image of F under F1 is F1X, then because this F1X belongs to capital X, so we can take its image under F2. So F2 will take it somewhere. So this element F2, F1X. And this is called the composition of map. So going from here to here is called the composition of map, and this is denoted as F1 composed with F2. So by F1 composed with F2, which is a new map, if I apply it on X, then it will give us F2 of F1X. And this is the composition of map. And you can see that if F1 is a map from X to X and F2 is a map from X to X, then F1 composed with F2 is a map from X to X. And because F1 is bijective and F2 is bijective, so F1 composed with F2 will again be bijective. So it means Symmex, it means O, that is the composition of map, is a binary operation from Symmex cross Symmex to Symmex. So Symmex with respect to this O, this is a group I. This is a group I. Now we will show that this composition of map is actually an associative binary operation. So take three elements F, G, H in Symmex, and now we will calculate this, and we will show that both are same. So we will show that both are same. So this is one map from X to X and this is another map from X to X, and we want to show that both the maps are equal. So for showing that both the maps are equal, we have to show that their images at each element of capital X are equal. So take any arbitrary X in X, then let us calculate the images. So by the definition of composition of map, see, F1 composed with F2 applied on X means F1X and F2 is applied on it. So here we can write Hx and apply G composed with F on it, and by the definition of G composed with F, we have G is applying on Hx and whatever is coming, F is applying on it. So we can write it as F, and G is applying on Hx means H composed with G applying on X, and then this can be written as F composed with G composed with H. This is applying on X, and this is true for all X. You can put one bracket here also. So it is true for all x means this map is equal to this map. So hence we can write that these two maps are equal. So this operation is associative. Now I am coming to the identity element. So we know that we have a map I from x to x defined as I of x is equal to x. So it is clearly bijective map, and usually people call it identity map because it is sending everything to itself. So now suppose I take f in Symmetric and I compose this f with this map and take the image of x, then this is f applied on ix and ix is x, so f applied on x, so it is fx. Now similarly, if you take this applied on x, then this is I of fx, but I of anything is that thing itself, so it is fx, and this is true for all x, both the identities are true for all the x, so I can write I of f is equal to foi is equal to f. So this means this I, which is a bijective map, this is the identity element of Symmetric. This is the identity element of Symmetric. So Symmetric is a monoid. Now we will see what is the inverse of an element in Symmetric. So for taking inverse, now take any element f in Symmetric. So suppose I take again f in Symmetric. Then because f is a bijective map, so there exists a map f inverse in Symmetric such that by the definition of bijection of map, there exists inverse map such that whenever you will compose f with f inverse, you will get same thing as f inverse with f, and that is equal to identity. Okay, so what is actually f inverse? If f is a map from x to x, then f inverse is a map from x to x, here to here, and if a is going to b, then f inverse is sending b to a. This is f inverse. So clearly, when you will compose these two maps, a will go to b and b will go to a, so a will go to a. So identity map will come. So inverse always exists in case of bijective map. So inverse exists. So it means sim x with respect to composition of maps forms a group. This is a group. Now for example, suppose I take a set x to be 1, 2, 3. Suppose I take x to be this set 1, 2, 3, then Symmetric is the set of all maps from the set 1 to 3 to 1 to 3 itself. So Symmetric is actually the set of maps from the map. This Symmetric is the set of maps from x to x. So we need to determine how many bijective maps from x to x can be determined. So if we want to determine a bijective map from x to x, so this is a set x, this is a set x, and 1, 2, 3 is here. So for having bijective map, I can send this 1 to 1 to 1 to 2 or 1 to 3. But as soon as I will send 1 to somewhere, then we cannot take 2 to that element because then that map will not be injected. So 2 has remaining 2 elements as a choice. Then 2 can go to the remaining 2 elements. And as soon as I set 1 and 2, then 3 has only one choice. the remaining element. So 1 has 3 choices, 1 can go to anywhere 3, 2 can go to, after the choice of 1 only 2 element, and after the choice of 1 and 2, 3 can go only to 1 element. So we have 3 choices here, 2 choices here and 1 choices here, so we have 6 choices. So we will get 6 maps from X to X. And what are these 6 maps? Let me write on these 6 maps. So suppose F1 I take, so 1 can go to 1, 2 is going to 2, 3 is going to 3, this is one map. F2, so 1 is going to 1, then 2 has 2 choices, 2 may go to 2 and 2 may go to 3. So I have taken 2 is going to 2, so now take 2 is going to 3, and then again 3 has only one choice, 3 can go to 2. This is another element. So now third element. So now let me take 1 is going to 2. Then 2 has 2 choices, 2 can either go to 2 or 2 can go to 3. So 1 is going to 2, for 2 has 2 choices, but 3 has not 2 choices, sorry. 2 can go to 1 and 2 can go to 3. Yes. So now 3 has only one choice, 3 can go to 3 because 1 and 2, 3 cannot go to 1 and 2. Now here 3 can only go to 1. So let me write it as F4. And then F5, 1, 2, 3. So 1 is going to 2, 1 is going to 1. All the possibilities has been exhausted. So now there is only one possibility, 1 can go to 3. So when 1 is going to 3, then there are 2 possibilities for 2. 2 can go to either 1 or 2 can go to 2. So 2 is going to 1 and 1 is going to 3, then 3 has only one choice, 3 is going to 2. And similarly here 3 has only one choice, 3 can go to 1. So these are the 6 elements. And now there is no more choices because we have taken all the choices. 1 can either go to 1, 1 can go to 2 and 1 can go to 3. And there is no more choices for the images of 1, so no more maps are possible. So these F1, F2, F3, F4, F5, F6 are the 6 maps. These are the 6 maps. Now the problem is how to compose this map. So suppose I have this map F1, F1, let me take another map F2, and I take another map, suppose F5, 1, 2, 3. So how will we compose these 2 maps? So under F2, 1 is going to 1, 2 is going to 3 and 3 is going to 2. Now what about F5? 1 is going to 3, so this 1 is going to 3, 2 is going to 1 and this 3 is going to 2. So it means finally this 1 is going to which element? 3, and this 2 is going to which element? 2, and this 3 is going to 1. So 1 is going to 3, so and 2 is going to 2 and 3 is going to 1. So this is actually F6. So we can say that F2 composed with F5 is F6. Please keep in mind that F2 composed with F5, it is F2 is first and then F5. So F2 composed with F5 is F6. So in this way composition of map can be done. But this is very long way of writing these maps. It takes too much space. So let me introduce a short notation for it. Now see, in this F1, 1 is going to 1. So I am writing 1 here and close the bracket, means 1 is going to 1. 2 is going to 2, so I write 2 and close this bracket, means 2 is going to 2. And then I write 3 here and close this bracket, means 3 is going to 3. Now see this F2. In this F2, 1 is going to 1, 2 is going to 3, 2 is going to 3, and 3 is going to 2. So I close this bracket. Close this bracket means 2 is going to 3 and 3 is going to 2 and 1 is going to 1. So I want to short this notation. This is taking too much space, so I am introducing a short notation for it. Now 1 is going to 2, so I write 1 comma 2 means 1 is going to 2. 2 is going to 1, so I close this bracket, and 3 is going to 3, so I close this bracket. 3 is going to 3. For F4 again, 1 is going to 2, 2 is going to 3, so I write 3 here. So 1 is going to 2, 2 is going to 3, and 3 is going to 1, so I close this bracket. Now for F5, 1 is going to 3, 3 is going to 2, and 2 is going to 1, so I close this bracket. Now for F6, 1 is going to 3, 3 is going to 1, so I close this bracket, and 2 is going to 2. So if in place of F1, which is too much, 1 is going to 1, 2 is going to 2, 3 is going to 3, if I write in short 1 bracket means 1 is not going anywhere, 2 is not going anywhere, 3 is not going anywhere, means 1 is going to 1, 2 is going to 2, and 3 is going to 3. For F2, this bracket 1 and this is 2, 3 means 2 is going to 3, 3 is going to 1, 3 is going to 2, and 1 is going to 1. 3 is going to 3, 1 is going to 2, 2 is going to 1. 1 is going to 2, 2 is going to 3, 3 is going to 1 under the map F4. 1 is going to 3, 3 is going to 2, and 2 is going to 1 under the map F5. And 1 is going to 3, 3 is going to 1 under the map F6, and 2 is going to 2. Okay, so let me do one thing. So for F1, I write as 1, 2, 3. For F2, I write as 1, 2, 3. For F3, I write as 1, 2, and this is 3. For F4, I write it as, so 1 is going to 2, 2 is going to 3, 3 is going to 1, and for F5, I write it as 1, 3, 2, and for F6, I write it as 1, 3, and 2 is fixed. 2 is going to 2. Now, so for F1, F2, F3, F4, F5, F6, we can write these symbols, but there is still a chance of simplifying this thing, because see, this 1 is not going anywhere. So if I write it as 2, 3 and say that whatever the symbol is not here, that is going to itself. So it will be enough to write 2, 3 for F2. In F2, 2 is going to 3, 3 is going to 2, which is shown here. 2 is going to 3, 3 is going to 2, and whatever is not written here is fixed. So let me leave this thing and write it in more simplified way, that is 2, 3. Similarly here I am writing as 1, 2, and 3 is missing means 3 is going to 3, and this is 1, 2, 3, and this is 1, 3, 2, and this is 1, 3. So it can be written like this. Now here everything is fixed, so let me introduce a notation like this. Empty bracket means nothing is there, means everything is fixed. So everything is fixed. So we can write the elements of Symmetric like this. So sim x, where x is actually 1, 2, 3, so I can write sim of 1, 2, 3 is equal to, so F1, in place of F1 I can write this. This is working as identity element, so everything is fixed because, and this is F2, that is 2, 3. Now F3, 1, 2, and F4, 1, 2, 3. And then F5, that is 1, 3, 2, and then F6, that is 1, 3. So these are the 6 elements of sim 1, 2, 3. This is called the symmetric group on the set 1, 2, 3. Similarly, if you take another set sim ABC, suppose I change the symbol and in place of 1, 2, 3 I write ABC, then again the same thing will work, and we can write it as AB, AC, and BC and ABC and ACB. You can check it. So in place of 1, 2, 3, if I write ABC, then it will be written like this. Now one more thing. Suppose I have 4 elements in the sets. Suppose I take sim 1, 2, 3, 4. So how many elements will this set have? This symmetric group have? So I have 4 choices for 1. If you will see after fixing the choice for 1, then 2 has only 3 choices, 3 has only 2 choices, and 4 will have only 1 choices. So 4 choice here, 3 choice here, and 2 choice here, and 1 choice here. So you have 4 factorial, that is 24 choices for the mappings of sim 1, 2, 3, 4. So if you will see, the cardinality of this set means order of this set should be 24. Similarly, you can show it that if I take 1 to n elements, then it will have cardinality n factorial, because 1 will have n choices, 2 will have n minus 1 choices, 3 will have n minus 2 choices, and so on. So there will be total n factorial maps in this set. Similarly, if you are taking any set having cardinality n, then sim of x, the order of this set will be n factorial. Okay. So one more thing, let me give you how to compose this element, and then I will move towards the next example. So suppose I take 2 elements 1, 2, 3 and 2, 3 in sim 1, 2, 3. Then how to compose it in this new notation? So suppose I take 1, 2, 3 and compose with 2, 3. Then what does it mean? This is one map, this is another map. So I will apply first this map and then this map. So we will see where the images of 1, 2, 3 are going, and then we can determine the composition. So suppose I am taking one element symbol. So 1 is going to 2, 1 is going to 2, 2 is going to 3 through this map. So 2 is going to 3. So finally 1 is going to 3. So I write 3 here. Now see where the 3 is going to 1. And in this map 1 is going to 1. So finally 3 is going to 1. So this bracket is closed. And now what about 2? 2 is going to 3. And 3 is going to 2. So 2 is going to 2. So bracket is closed. So this is simply nothing but 1, 3. So in this way you can compose the elements of sim 1, 2, 3 or sim 1, 2, 4 or another symmetric group in the simplified notation. So I am not going to the more details of symmetric group here, because we don't know till now. I have not defined the subgroup, normal subgroup and order of the element. But afterward I will give lectures on symmetric group, which will cover the details of symmetric group. Okay. So now we are going towards the next example. Now come to the next example, example number 14. So let as we set this rho S is the power set of S. Power set means set of all subsets of S. So now define a operation delta from rho S cross rho S to rho S as for as if I take two set AB, then A delta B means it is defined as A minus B. This is set minus union B minus A, and it is usually called symmetric difference. Symmetric difference. Symmetric difference of these two sets, and where AB belongs to rho S. And one can can easily check that this rho s with respect to this symmetric difference forms a commutative group. This is a commutative group. Commutative group. And what will be the identity element for this set? Means, suppose A I am taking, then I want to find a subset B such that asymmetric difference B is A itself. So it means A minus B union B minus A is equal to A itself. So if you take, just check it, if I take B to be 5, then A minus B is A and 5 minus A is again 5, so the union will be A. So this element, this is working as identity element, and now what about asymmetric difference A? So you can say A minus A union A minus A, so that is 5. So this is working as, so the A inverse is always A. So identity exists, inverse exists, associativity you need to check. So for associativity, if you take 3 sets, so take ABC in this set, then you need to check asymmetric difference B, symmetric difference with C is same as asymmetric difference B, symmetric difference C. So I am leaving it as exercise. You can verify it using the Venn diagrams of Venn. So you make the Venn diagram for this and this, you will get that the shaded parts are equal, so both will be equal, and there is a proof for it. So this operation is associative. Phi is working as the identity element, so this phi is identity element, and each element is self-inverse, and of course by definition it is a commutative because asymmetric difference A, asymmetric difference B is same thing as B symmetric difference A, because it is the union of A minus B and B minus A, so both are same thing. Either you write A before or B before. So this is an example of a commutative group. Now next example, example number 15. Example number 15. Example number 15, the example is dihedral group. I am not going to introduce this example right now because there are several things with this example attached. So actually it is a group usually denoted as Dn and called the dihedral group of order 2n. So I will introduce this group later on.